SwayamPrabha. Digital India. Educated India.
So, this is the 7th lecture. Okay. So, let us look at the generalized governing equations in multiphase systems. Sorry, what happened? Just one second. Okay. So, the generalized governing equations in multiphase systems. Okay. So, you guys have all done single phase system analysis, okay, for a long time, and you know that there are 3 conservation laws, essentially: conservation of mass, conservation of momentum, and conservation of energy, right. So, conservation of momentum is basically nothing but the Navier-Stokes equation, okay. Conservation of mass is conservation of mass, and conservation of energy comes from the first law. It is the same as the first law of thermodynamics, okay. And in addition, people who have taken like reacting flows, say for example, not necessarily multiphase flows, they have also dealt with multi-component systems or multi-species system. They also have done the species balance. Species balance and your energy balance looks pretty similar because both are scalar quantities. Okay. So, the momentum equation, of course, there are 3 momentum equations, okay, and there is one conservation of mass equation, right. So, that makes it basically 5 equations including energy, and for species, as many species you have to have, for example, if you have 5 species in the system, you need to have 4 equations, because the 5th one is not needed because you already have the mass conservation, right. So, these are the so we are going to, what we are going to do is that we are trying to see that how these equations can be generalized in the case of multiphase systems, essentially. Okay. So, what are the multiphase systems? What are the requirements of the multiphase system, right? So, multiphase system is distinguished, if you look at the slide, is that multiphase system is distinguished from single phase systems by the presence of basically one or more interfaces separating the phases. Okay. So, it can be considered as a field that is divided into single phase pockets by these interfaces, or these interfaces can actually move, they may be deformable, there can be transfer of mass, momentum and energy among the phases itself, that can also happen. Okay. It may not happen also because it could be just the 2 phases may be benign with each other, they do not actually interact. It can be several types of things, but it is basically one or more interfaces are separating the individual phases. And so, there are like single phase pockets, there are regions. No, I am not saying what is the extent of the single phase regions, it could be very small, it could be very large, but there are regions. Okay. Now, if you look at the macroscopic and integral formulation for this kind of a method, you find that a fixed mass system, if we take a fixed mass system, describes an amount of matter that can move, flow and interact with the surroundings. Whereas, on the other hand, a control volume approach, a fixed mass system is a fixed mass system, there is the amount of matter, it is like an arbitrary. So, if this is the fixed mass system that you have, okay. The control volume, however, depicts a region or volume of interest in a flow field which is not unique and depends on the user. So, I can define my own control volume. Okay. So, conservation laws for a fixed mass system needs to be transformed to apply to a control volume framework, right. So, if you look at this nice little picture over here, you will find that that is the fixed mass system, right, and that is the control volume that we have considered. Okay. So, what happens is that this control volume in the fixed mass system basically moves. So, this is at time t equal to t, this is the fixed mass system at time t plus delta t. Okay. So, the control volume can be made to be fixed, this fixed mass system is actually moving, okay, around it. So, let us look at now the situation over here. Okay. So, this is a little bit of a busy slide, but we will walk through the steps. Okay. Let us for the time being consider that there is only one phase present, okay, and that is the kth phase. Okay. And so, for a system with fixed mass, the change in general property, right, that the change in the general property is basically nothing but any property. This property is like phi k, this property can be anything, right. So, we will see later it can be momentum, energy, whatever that you can think of. For the time being it is some property, some generalized property which is given by phi k. This phi k of the system, change in phi k of the system is basically nothing but the change in phi k at time t plus delta t minus whatever was the phi k at time t, and this is divided by delta t. Okay. And this is k I have written at phi k, where k actually basically denotes the kth phase. Okay. Do not be bothered about the phase right now, just take that here k is almost like the single phase. Okay. So, considering the control mass occupies region 1 and region 2 at a time t, right. So, at a time t, if you consider this, there is a region 1, there is a region 2, right. So, in region 1 and 2, this phi is basically phi at time t equal to t, that means phi at t is basically nothing but phi 1 plus phi 2, is not that so? It is sum total of this plus this, is not that so? Okay. Now, at time t plus delta t, what happens? That means, after some time the fixed mass system now occupies 2 and 3. Do you see that? It has moved from 1, it is now occupying 2 and it is occupying 3. Okay. So, it is almost like phi t plus delta t now is basically phi 2 plus phi 3, correct. Okay. Therefore, now the rate of change of whatever that property of the system is given by basically two quantities, right. So, it is the change in region 2 at time t plus delta t minus dt, right, and it is the change of between region 3 and region 1, right. That is what actually happens. Now, if you look at the third and the second and the third term of this expression, this and this very closely, what does it show you? It shows basically the rate of change of property within the control volume, right. Is the represents the is the second and the third term on the right hand side of the equation represents the property that is leaving and entering the control volume due to mass flow across its boundary. Look at it very carefully. If you look at the control volume, okay, you can find that 3 is the mass that has. So, 1 is the mass, 1 is this particular shaded region, right. Okay. So, if I change the color of my pen, let us say I use black now, okay, black will be. So, and this is the region 3, correct. Okay. So, one represents a mass in, one represents a mass out. Okay. If you consider it in that particular way, when the control volume, when this system has actually moved, right. Okay. So, that the second and the third term represents respectively the mass leaving the system and the mass that is entering the control volume. Control volume, remember, it's I am not talking about the fixed system, the control volume part. Okay. So, this is the control volume, right, that we drew, right. So, there has been some mass that has left the system. Left the system means this is the mass that has left the system, right, and this is the mass that has entered the system, correct, is not that so? So, the control volume is fixed, this fixed mass has come and moved, right, this fixed mass is transiting through the control volume, right. So, what happens is that as this fixed mass transits through the control volume, this region 3 over here is basically the mass that is leaving the control volume, correct, whereas 1 is the mass that has entered into the control volume, correct. So, so that is the thing that we have stated over here. Okay. Whereas, this particular expression over here represents the rate of change of property within the control volume, because region 2 becomes coincident with the control volume as dt approaches 0. Look at region 2 now. Okay. Now, in region 2, when dt, that means the extent of this time becomes very small, right, this region 2 becomes coincident, okay, with the control volume that we have drawn over there, right. So, this is nothing but the rate of change of property within the control volume, this particular term over here. Okay. So, now since we have established these two, okay, if you now look at the individual terms, that means the rate of change of this property in region 2, say for example, right, okay, which is given by the rate of change of that property within the control volume, right, that is given nothing by the rate of change of property within the volume, correct. So, that is why we have written it as rho k phi k into dV. That means, whatever is the volume and it is integrated over the volume. So, the rate of change of that property within the volume, right. On the other hand, these two terms which we said are the flux terms, right, these two terms we already said were the flux terms, they are represented by the flux, right. The flux is what? That property is transported by some velocity, okay, across the control surface. This is the control volume. So, these are basically the control surface, right. So, this is the mass or momentum or energy, whatever it is, this is transported porting this phi k across the control surface. And why we have written it as V relative? That is because let the reference frame move with a constant velocity and the control volume may move with the reference frame. Okay. So, if the reference frame velocity is equal to 0, this becomes the same as the absolute velocity for the kth phase. Otherwise, if the control volume is moving with the reference frame, we have to take that out. Okay. So, this is basically nothing but the V relative. So, the control volume is moving with the reference frame. This is what the control, this is the relative velocity with which the mass, energy or momentum or whatever that is that phi k represents is entering or leaving the control volume. Okay. So, if you combine this term and this term now, okay, if you look at the presentation, if you combine these two terms, we find that the system, the rate of change of that property in the system is given by the volumetric change, right, or the rate of change of that property within the volume, plus there is a flux term. Okay. Flux term transports whatever it is that it is transporting across the control surface, right. Okay. So, this form relates the rate of change of property for a fixed mass system with that of a control volume. Got it? So, essentially this essentially means that there is a control volume, the fixed mass is actually moving across the control volume. So, this region 1 and region 3 basically represents the flux, whereas region 2 is basically whatever was there within the control volume always, right, it is there, right. So, the change in region 2 is essentially is whatever is the change of property inside the control volume, whereas region 1 is whatever is entering the control volume, region 3 is whatever is leaving the control volume. So, those are basically two flux terms. Okay. In the limit of dt equal to 0, of course, this is drawn in a highly exaggerated way. When dt is actually approaches 0, okay, this becomes region 2 becomes the control volume in itself. These are basically the flux term entering into the control volume and leaving the control volume. Okay. And whatever the flux terms have been represented by this relative velocity over here, accounting for that the reference frame moves with a constant velocity and the control volume moves with the reference frame. Okay. We have been able to cast this equation in this particular form, and this V relative is what is used over here, right. Okay. Remember that there is a dot product with Nk, where Nk is nothing but the surface normal. So, the velocity may have a direction, okay, angular direction, but the surface normal may have this, right. So, this is basically Nk dot Vk relative, right. Okay. So, it is the dot product between the surface normal and the velocity component. Okay. So, that is what it is. Remember, phi k can be a scalar, can be a vector, can be anything else, but this particular term that you see Vk relative into Nk, this is basically a scalar, right, because it is multiplied with a surface normal. Phi k that you see over here can be anything, okay. It can be mass, it can be momentum, whatever, we will see to that, okay. But on the other hand Vk relative, okay, dot Nk basically is a flux term which is perpendicular to the surface, right, that is what we need to take, and that is basically a scalar. Clear on this particular part? Now, if there are multiple interfaces, say for example, right, this is just for one phase that we showed, right. So, let us take this simple thing that this is a solid, this is a corresponding liquid, this is the corresponding gas. So, the interface, there are partitions, you can see this partition, you can see this partition. So, there are partitions across the interface, right, these are interfaces, and each of this has got their own individual surface areas, right. So, this has got a surface area of AS, this has got a surface area of AL, this has got a surface area of AG, right. So, the interfaces that separate the different phases, the volumes and the surface area of each phase are functions of time, got it. So, let us pull the, I do not know why the marker is not coming. So, the control volume however is fixed in space, okay, but these interfaces can move, right. So, this interface and the individual surface areas can actually move, right. So, what we can say is that the sum total of this volume should be V, because the control volume is fixed, right, and the sum total of these areas will be also fixed. It does not mean that these areas cannot vary, they can vary individually among themselves, but the sum total of the area is A, the sum total of the volume is V, got it, okay. And this was the example that we are showing you, that this is the surface normal, this is the velocity. So, whatever is the angle, you take the dot product over there. Now, analyzing, we already have analyzed the system, right, for this. Now, we are writing it for each and every phase, same term, right. Look at the term, this is the rate of change of that property, whatever that property is within the volume Vs. Vs is not the total volume, it is the volume that is reserved for the solid phase, right. Similarly, there is a volume that is reserved for the liquid phase, there is a volume that is reserved for the gaseous phase, correct. These are not the total volume, right. So, these are volumes like Vg, Vs, Vl, right. These are not the total volume, this is an important concept that you should remember. Similarly goes for the area as well, that you, for example, these are the different relative velocity components with respect to the gas phase, with respect to the liquid phase, etc. But these areas are once again these areas, right. So, that is an important consideration over here. So, we are basically the total rate of change of that property within the system is nothing but the sum total of all this, except that you have to know what are the areas that are occupied by the each individual phase. That means, you also have to know what is the volumes that are occupied by each individual phases, right. Okay. So, if we write the combined equation which is given over here, right. Okay. So, you can say for two phases there are basically 4 components, right. This is for phase 1, sorry, these two are for phase 1, these two are for phase 2, right. You can have a phase 3 also, but the important consideration here is that A1, A2, V1, V2 are to be decided. It is not that easy, right, because you do not know the extent, right, of each of the individual phases. If it is nice droplet in a pool of liquid or a vapor bubble in a pool of liquid, then you know the individual things, right. It is a very clean interface, okay. It is a very clean interface. We can write this equation very easily over there, right. It is very easy to write, but however, if you recall the problem that there are, say, lots of fluid ligaments, then there may be interstitial flows, right, all those things that happens, determining these areas and volumes becomes a practically a very onerous kind of a task, right. Okay. So, Let us quickly do the conservation of mass now. Okay. For the conservation of mass, what we do is that we take small phi k equal to 1, right, and the big phi k, right. This small phi k comes with a v relative. Okay. This phi k is taken as m, whatever is the mass of the system, right. So, we can quickly write this expression, which is basically the rate of change of mass within the system. This is the density of the kth phase and this is the corresponding flux term, right. So, since the mass of a fixed system is constant by definition and it contains only one phase, this is the expression. This is the all the mass conservation equation that you are familiar with, right. The mass conservation is what? The rate of change of mass within the system and whatever is the flux term, mass coming in, mass going out, right. Now, if it contains multiple phases, this is nothing but the sum total over all the phases. That means, if you see this pi over here, that is nothing but the number of phases, right, and it is the relative velocity and the corresponding surface area of each phase. AK is nothing but the surface area of each phase. Is that clear? So, this is the surface area for each phase, right. Similarly, when you come across to the momentum equation, now the control volume has say one single phase k for the time being. Okay. So, the integral form of Newton's second law, as you know, the momentum equation is nothing but Newton's second law. Okay. Phi k, capital phi k is nothing but mk into v relative. This is the momentum, mass into velocity, right. So, mk is the mass of the system, Vk relative is basically the momentum with which the flow is entering or leaving the control volume, right. And phi k, the small phi k is nothing but the V relative. This time it is a vector, previously it was a scalar, right. So, when you write this now, the Newton's second law of motion in an integral form, what we say, the right hand side once again is very similar to this, right, except instead of phi k we have this Vk relative, here it was 1, here it is Vk relative, right. It was 1, in here this particular value was equal to 1, is not that so? Okay. So, now here also you see Vk relative into Nk is nothing but a scalar, it is a scalar, right. Now, that scalar means this is nothing but the mass flux, right. On the other hand, this is a vector, right. So, this entire expression is of course a vectorial representation, right. So, but in the case of a mass, conservation of mass, this was entirely a scalar quantity, right, because that was a dot product. Here also this is the mass, this is nothing but the same as this, these two are exactly identical. That is now what is the momentum that is transferred across the interface, okay. And this is the rate of change of momentum within the control volume, right. And what is the left hand side that we have written? This is the sum total of all the forces that are acting on the control volume. Now, the forces that are acting on the control volume includes body forces like gravity and contact forces that act on the surface like your shear stress, okay, and things like that. It can be anything though, okay. So, the body force, if the body force that is acting on the ith species in the kth phase is x ki, if you cannot see it, this is x ki, okay, then the total body force expression is given by this, right. So, k is the individual phase, I can be the individual components, it can be also a multi component system. If the body force per unit mass is same for all the species and phase, as with gravity that is indeed the case, right, we can just simply write it like this, which is nothing but rho k x dV. So, there is no x k i's are all kind of x, right, because this is a gravity, right. And the stress tensor that is acting on the fluid control volume includes both normal as well as shear stresses, right. So, the total force is nothing but the body force term which is given by x k I and this term which is nothing but the total stress tensor. So, Nk is a normal local normal unit vector as we stated before. So, the entire equation when it is written is represented like this. N is the n here is the number of components. If you have n number of components, you can have n number of components in the system, not the number of phases though. Okay. Tau k relative is nothing but the stress tensor, the total stress tensor, and this is basically nothing but the change of momentum within the control volume and the momentum flux that is happening along the control surface. Got it? So, when the control volume has multiple phases, okay, integrations must be performed for each sub volume. So, once again we have the same thing, these areas come into the picture, these volumes come into the picture, right. The total force is summed across all the cases, all the phases. So, that is the final expression that we get. So, it is no different from this, except now we have this additional areas and these additional volumes that comes into the picture, right. Now, why it does not represent the Newton's normal Navier-Stokes equation that you are familiar with, because this tau k relative that we have, okay, we need to apply the constitutive relationships to get to the form that you are most familiar with, right. That is what you are most familiar with, right. So, those kind of forms like the shear stress type of forms, of course, this is only the shear stress component of it. This comes only from the constitutive relationships that we will see later. Okay. So, what we will do is that we will stop here in this particular lecture, and before we take on to the energy equation, let us try to digest these facts for the time being. What we have done is that we have taken a control volume approach, okay, and we have shown that in the control volume, okay, we can represent it by a general property phi k, that phi k can be momentum, energy we have not covered, but we will show that in the next lecture. But it all shows that how this mass, momentum and energies are actually distributed inside the how the transport actually happens. So, we have done conservation of mass, we have done now conservation of momentum also, and we have shown that where the stress tensor comes into the picture, it comes from the force, the total force. And we have also stated that this is equal to the rate of change of momentum within the control volume and plus whatever is the momentum flux that is happening across the control surface. Okay. So, the next class we just will finish this off, okay, and we will so we can do, and we will move on and see the end this integral formulation and then do the differential formulation and then see some of the averaging techniques that we can have. Okay. So, thank you. We will see you next class.